Alright, hell yeah. So, heck yeah, this is a video that I would like to reference. You know what I mean? And this is kind of the first time going through this. So heck yeah. So, there's a lot of things that we can represent in a simpler way. Because even right here, what I'm trying to do is this problem. And try to, so we have, it's like the toilet paper roll, rolling vertically, or like a disc rolling down a vertical wall, like on gears, or just like a disc that has wrapped around string and then it's unspooling itself. And so what I would like to say, and I should have drawn this a little closer, what I would like to say is, heck yeah, this right there kind of acts like a pivot, and then, maybe this cylinder we can say is just like three different chunks of mass. You know what I mean? I've done it with angular momentum, where if this is 1 kilogram, like this chunk of mass is half, this is a quarter, and then this would be a quarter. And then so if we go over here to our pivot, we can say we have a quarter of the mass there, half the mass there, and then a quarter of the mass here. But because this is the pivot, these are the only two that cause like a driving force with mg. You know what I mean? We have 1/2 mg and then 1/4 mg. But then heck yeah, this is like a pivot. So we come back here, and then maybe you could even just simplify this further, and just say, hey, maybe these two masses, you just put them at some distance, you know what I mean, there, and then isn't this that problem? But there's just one major error, and I made a couple of videos where I had this thinking, but it has to be improved just a little bit, because this is a pivot point, but as it starts to pivot, this pivot point constantly moves. So let's go over this. So if here's our circle, in 1 second, and let's say it pivots, sure, we're going to get some angular, so like right now, well, let's say initially the angular velocity is 0, it's stationary, you know what I mean? The center of mass, that velocity is 0 initially. Okay, 1 second later, we know, just from the equations, that this thing has an acceleration of 2/3 g. Kind of a fun equation, fun one to do. But heck yeah, so that's just a known quantity that we can use. And what this tells us is that hey, the center of mass after 1 second. What is this? This is 2/3 times 10 meters per second squared. So we're going to have, what is it? Is it 6.6? Yeah, we're going to have 6.6 meters per second squared. That means we're going to have a change in velocity of 6.6 meters per second for every 1 second. So this is times 0. After 1 second, heck yeah, we're going to have a velocity of now this thing's trucking. We're going to have a velocity of 6.6 meters per second. And then what else? Oh yeah, and it had an omega of 0, but now we're definitely going to have some sort of omega. And the cool thing about rolling discs, you know what I mean, even just without slipping, is you can totally find the omega just by figuring out how far you went, you know what I mean, and that's how is that related? Well, we do have a radius, and so what we want to find is and then you compare it to just a disc just spinning like on a platform. So if this thing's spinning with some sort of omega, we know like, hey, these are our tangential velocities, and these tangential velocities are that's omega times r. That's the definition of tangential velocity. I like to say radians per second times radius. Because radians are kind of unusual, but radians times radius gives you something normal. That's going to be tangential velocity, and it just happens that whatever the tangential velocity is for this disc on a stand is going to be the same angular velocity in radians per second, just of the actual velocity of the center of mass. this velocity, and because you can't say this point has any velocity, that's stationary, but it does roll out. The other thing is like, hey, it rolls out, you know what I mean, on arc length, you know what I mean, but anyway, I think we get it. So, but what the hell? Oh yeah, no duh. So sometimes it's good just to write an equation, you know what I mean? So we're trying to find this omega at times equal to 1 second. So omega times radius. You know, radians times radius is something normal. That's velocity tangential. We know velocity tangential right here is 6.6. We want to solve for omega. So let's do that. Simple equation, but you just solve for omega. So we got omega, tangential velocity divided by the radius. You know what I mean? For most problems, we just keep the radius 1 meter. So now we know our omega is going to be 6.6 radians per second. And all right, hell yeah. So this gets into the meat and potatoes of kind of what we're doing. And the bummer about even just things in free fall, hey, they have like a you know what I mean? We have an angular velocity of 6.6. We went from 0 to 6.6. You know what I mean? So in 1 second, so if this is the case, it's just like velocity. If we're going 0 meters per second here, and then we're going to go 6.6, our average velocity of this was 3.3 meters per second. We did it for a second, so the distance that we travel between here and here is going to be 3.3 meters. And then you can use that same logic when dealing with radians per second. So if my angular velocity is 0 radians per second, and then after 1 second we got 6.6 radians per second, our average radians per second over that second is going to be 3.3 radians per second. And the same thing, just like we found distance here, it's just that no one wants to find radians, like no one cares, you know what I mean? But sometimes we have to, and so we say, what was our radian like how many angles did we go in radians? Well, in that 1 second, because we have an average velocity of 3.3, we went 3.3 of them. Okay, so here's a circle, and you divvy up a circle 6 times. Basically, each of those is 1 radian. So after a second, you went 3.3. Heck yeah, you're right there. So that's what happened after a full second. Now here is, I really like doing problems in acceleration where, hey, you just take 1 second. Because, you know, usually you get a term for acceleration. Let's say it's 10 meters per second squared. Well, hell yeah, you can totally change this into meters per second, and then what does this even say? It says that if my velocity is 0, in 1 second my velocity is going to be 10 meters per second. So if you just take a time frame of like 1 second and you start with something that's at rest, you know what I mean? Hey, this number is you're going to be your velocity, which is super cool. You know what I mean? So it's just kind of I kind of like that. So, but what I'm getting at is like, we could do that for like a free fall. Like, hey, let's take this mass and then have it drop off a cliff, and then what's going to happen after 10 seconds? What's going to happen after 1 second? Well, it has a velocity of 0. After 1 second, we have a velocity of 10. Average velocity of 5 meters per second, and we did this for a second, so it must have gone 5 meters. So cool. So what I'm getting at is that these distances are usually pretty large in free fall. So the only way to make a problem like this kind of make linear sense is if this thing doesn't fall very far. You know what I mean? So if we do this, if we say, hey, this is like really far out. Like if we're going to drop 5 meters, you know, maybe this is 500 meters. And then the problem gets nonsensical because this would be a massless rod out to 500 meters, and then you're just sporting 1 kilogram. But if this is the case, this is going to, and then let 500, let's see, if this is 500, maybe this is 100, this is 50, this is 10. Yeah, we made this too big. But anyway, let's say we made this 50. And then so we divvy this up 10. You know what I mean? This is 5, and we go 1, 2, 3, 4, 5. So heck yeah. So this is 1. I mean, no, this is 5 meters, and this is 50 meters. So heck yeah. So now this thing just falls that far. So visually we have a picture where this thing just falls there, and it looks like it falls vertically. And that's kind of what we're getting at. Like we're wanting to take a problem like this and then just have it fall vertically. Because if I do this, heck yeah, I know the forces on it. It's going to be mg, and then there's no other forces in the y direction. So then when this falls, it's basically going to fall vertically, you know, until this tension, you know, makes it swing in. And when that happens, like if it's down here, hey, gravity isn't moving it that way no more. But right now, gravity is moving this thing with a tangential velocity. So, and after 1 second, we know that its velocity is 0, and then heck yeah, right here we know our velocity is 10 meters per second. So in this case, heck yeah, 10 meters per second for our velocity. Velocity is 0 there, and then we know our average velocity is 5 meters per second, and so we know that this distance is 5 meters, and then that's why we did this to be 50 meters. But just, yeah, that's the only bummer about doing something like this, is that, I don't know, you kind of have to explode the numbers just to make it make sense. Because what we don't want is after 1 second this thing to go 3.5 radians, where you're just like, what? After 1 second it's like way over here? It's just like, no, because gravity isn't going to, you know what I mean, the simplified model. Yeah, the simplified model is only going to make sense for like this first initial, you know, second. And I don't want to change my seconds, my change in time to be like 1,000th or 100th of a second. I just don't want to do that. I just want to work in 1 second intervals, because usually you get a number for acceleration and you're like, hell yeah, after a second I'm going to move that distance. But what we're doing here is we're trying to get radians. You know what I mean? So if, like, what's the radian? And that's where we can't have 3 radians. We want like a very, and then a 30-degree angle is 0.5 radians. So we definitely want to be within 0.5 radians. You know, I mean, maybe like 0.1 or something. So let's find the radians. So we know that radians times radius is tangential velocity. We just found our tangential velocity as 10 meters per second. Cool. And then so we can figure out what our the angular velocity is after 1 second. That's omega. That's tangential velocity divided by radius, and so that's going to be, for this problem, is going to be 10 meters per second divided by 50. And sweet. So we're going to have 1 divided by 5, or 0.2 radians. Okay, so we're right in that ballpark of like, hey, something fairly visual, and it looks basically like that. You know what I mean? That would be 0.2 radians. This is 5 divided, inverse tangent 5 divided by 50. It's a 5-degree angle, 5 to 6 degrees. Okay, so heck yeah. So now we have our problem kind of making sense. Cool. So now we can move on to and yeah, that's kind of what you're doing. We're trying to simplify a problem into kind of linear motion under the forces of gravity, finding our angular velocity, and we know that our angular velocity at time 0 is 0, and so just even finding tangential velocity based on the acceleration equation, F equals ma, and we have the driving forces being gravity, just mg is equal to ma. You know, I mean, heck yeah, we have a very simple problem where we can find acceleration, and then after 1 second, say that's the velocity, and then we can use that to figure out, how do we do this? Oh yeah, so we know, we use this equation to figure out our angular velocity. And then we know that we had initially 0 angular velocity, and after 1 second we got some. So now we can figure out our angular acceleration if we wanted to do that. Yeah, so just a lot of cool things. But mainly, mainly what happens is you'll get a problem like this. Like this is the one that I wasn't able to solve. You know what I mean? You kind of have this thing, you know what I mean, with that, and then you got two little wires on it, and they're off center. There's nothing supporting this axis, and then here, then you have another mass, you know what I mean, mass A, and so now this thing, it looks like it has a pivot right there, where you can just, hey, let's take this pivot, and then let's say we have a chunk of mass over here, and then a bigger chunk right there, and then maybe a chunk right there, and then it's just all connected to a rod, and then here's our pivot point, and then you know what I mean, hey, these cancel, so then we can figure out that we maybe have a driving force, yeah, stuff like that, and then kind of due to continuity, you might be able to find just one location for this mass over here, and then you can kind of treat it like our problem like right here, and then you might be able to find the angular acceleration after 1 second, just like we did. And if you knew that and it started from rest, then you could figure out the angular I meant velocity, but then you could figure out the angular acceleration. And then from that, you know what I mean, if you figure out the angular acceleration or just the omega after 1 second, heck yeah, you'll be able to find the acceleration of in any of these points. So that was the deal for this problem. You needed to find the angular acceleration of this point, but you had to find the omega first and then find that radius. But you couldn't treat it like a pivot problem like this. And then that's kind of the next thing that we're going to talk about. And then, I mean, actually, it'll probably be a pretty short video because we're not going to do any technical problems. We're just going to bring up and introduce the idea. So we're going to use this scenario where we have, it's like, what did we have? We had 1 kilogram out at 50, and we were able to go 0.2 radians. Okay, so let's set that problem up. Okay, so we're going to go out 50. And we have this 1 kilogram mass. All right, cool. And then we found that it you know what I mean, it went right here. And we had radians of like 0.2. Was it exactly? Probably not. Oh, I didn't even solve it. No, it was. Yeah, it was 0.2 radians. So we have 0.2 radians per second. Was our omega after at t equals 1 second. That was this 0.2. Okay, so but what a lot of these problems happen is they're just like this problem. Is that sure you have a pivot point and you could treat it like that, but you can't because this pivot point is also moving downwards. So when this mass has a force of mg on it, you know what I mean? Well, let's say it's 1 times 10. That's going to be 10 newtons. That applies to this problem if this is stationary. But then I do like 3 different scenarios, and maybe we'll just do at least one. Let's say we drop this. This is actually like a bar, and you're actually holding it in place. But then you know, in this scenario, you're holding it. But then all of a sudden, you just let it go. So you hold both sides, and then just let it go, and now it's free falling. So what's our angular velocity? Nothing. Like both these things, this whole system is just moving. Where it's not going to. So yeah, that's kind of the easiest one to visualize. And that's an important one, because then we're going to say, well, let's say it's stationary, it does this. But now let's say I like to do half. So we're gonna take this thing and put this thing into a machine that has a sliding track that will actually slide along at half of gravity. So if gravity goes every second, it's going to go 10 meters per second. You know, a change in velocity, it's going to go from 0 to 10 meters per second after 1 second to 20 meters per second. Well, this is going to be half that. It's going to be 5 meters per second per second. So, and that's this machine. And then so what are we going to experience? Well, I'll just spell it out. We're going to experience half this, this after 1 second in this machine. We might be down here after a second, but then our angular, our omega, you know what I mean? So so we're going to start here, end here. We still start with 0 radians per second. That's our angular acceleration. But after 1 second, our angular acceleration is going to be 0.1 radians per second. And it's because, like, well, one method, because I did a whole video on like pulleys where I was just like, hey, you can just visually see that from this scenario to this scenario, it's like there's no force. So we identify that this has a mass, and it has a force of 10 newtons due to mg. But then if it's in free fall, I'm just you know, just mentally I'm like, well, it's like it doesn't have a force. Now that's not true, because this is a mass and we still have an earth underneath us. Kepler's equation does not go away, so I better write it, just because what we're doing is kind of like a little mental shortcut. And I don't know, I'm trying to set up these mental shortcuts to you know, just have a better understanding, a better intuitive understanding of how problems are working. So I don't get, you know what I mean, just caught up into the equations. All right, so force of gravity is gravitational constant. This mass times the mass of the Earth divided by the radius of the Earth squared. All these three terms are just g, and so we got mg. Because we have a mass and we have all those things, we're at that radius of the Earth, the mass of the Earth is underneath us, gravitation is a constant, and so this never goes away. So, and I don't know if I can actually do the technical side to this equation. I'm sure I can, but just from the pulley video, I can just easily say, oh, this thing's accelerating at 5 meters per second. Well, cool. It's like it has half of this. So let's set up that scenario where we have 5 newtons. So we're going to do F equals ma. Now this mass is still the same. That did not change. It's still 1 kilogram, but we have 5 newtons over here. We have 1 kilogram, and then we want to know what the acceleration is. So we can definitely see the acceleration of this is going to be 5 meters per second. And it's not going to be 10. This was 10 meters per second. This was 5. Now don't get it confused with this 5, because I think... yeah. So I mean, we're just doing the halfway point, but we'll do one where this is 3.3. That's usually the one that maybe we'll just do 3 meters per second. Cool. Okay, but to finish off this one, so now after 1 second, this has a change in velocity. So this thing is going 5 meters per second. Initially it was going 0 meters per second. Its average velocity was 2.5 meters per second. So cool, it went a distance of 2.5. We know at this point the tangential velocity is 5 meters per second. So we can know our omega, because omega r is equal to tangential velocity. So omega is tangential velocity divided by r. That's 5 meters per second. And in our problem, this is 50 meters. Cool, so we have 5 divided by 50, that's 1 divided by 10, so now we have 0.1 radians per second. So that's our angular velocity. And for this problem, our angular acceleration, well, we have a change in 1 second from 0 to 0.1. So we have 0.1 radians per second squared. Cool. And that's why it's just very useful to do a problem in 1 second, because whatever your omega changed, well, hell yeah, that's going to be your angular acceleration. Okay, so we'll do this one more time with like 3 meters per second, just because, so check this out. So if we have this statically, we're going to have 10 newtons on it. If it's in free fall, we're going to have 0 newtons. And then if it's half, we're going to have 5 newtons. So what's the equation there? Because now let's do 3. If this acceleration is only moving 3 meters per second, well, like it would be a mistake to say we only have 3 3 newtons on there, because that's not how it works. If this isn't moving, we have 10. It's like we have 10 newtons on this mass, which we do. But if it's moving just a little bit, like even at 1 meter per second acceleration, well, it's like we have 9. Maybe it's like we have 9 newtons on this mass. So yeah. So if we only have 3, we're going to have a higher number than 5. So we need an equation for that, and it's just kind of a linear ratio. But I would do this: 10 minus 3 divided by 10. So that's going to be 7. That's going to be 7 divided by 10. That's going to be 0.7. So this would be this would be the ratio. So whatever this was, mg, we're going to multiply it by 0.7, and we'll get 7 newtons. Hell yeah! All right. So let's do that scenario. So we have 50 meters. We have our 1 kilogram, and now this whole reference frame is accelerating at 3 meters per second. We have 1 kilogram, so we have a force of gravity, and then now we're just going to use kind of that, like, hey, normally we would just have 10 newtons, but because we're moving this way at 3, we're going to have 10 minus 3 divided by 10. That's going to be a multiple of 0.7. We're going to have 0.7 newtons. So now this problem looks like, it's like it feels like it just has 7 newtons on it. And so now we're going to use F equals ma. Now this mass doesn't change, so we have 7 newtons on a mass of 1 kilogram, and now we have an acceleration of 7 meters per second. So if this reference frame was going 10, and this acceleration is the acceleration of this compared to the actual compared to the actual assembly. Like if you're an observer on this assembly, this is how it's accelerating. Okay, so from that, the acceleration is basically change in velocity, change in time. So after 1 second, it's going to be moving 7 meters per second. Cool, so that's going to be its tangential velocity. Omega r is velocity tangential. So omega is velocity tangential divided by r. And we have 7 meters per second divided by 50. And we got 7 divided by 50. And so we get 0.14 radians per second. So if this was moving 5 meters per second, we got 0.2. No, we got 0.1. If this wasn't moving, we got 0.2. And now if it's moving a little bit, we get this. All right, hell yeah. And so now what we did from the pulley problem is we solved this from the kind of the technical standpoint. We still have a mass of 1 kilogram. And so saying that this has a force of 7 newtons is probably not true, like, at all. It's just visually can make problems easier. So what actually is happening? So we still have this acceleration of 3 meters per second. Now we're going to do a free body diagram. We're going to chop this thing, put it over here. On Earth, we still have an Earth underneath us, so we have a force on here. That's the known force. We have a force of gravity of 1 kilogram times 10 meters per second squared. That's going to be mg, and that's going to be 10 newtons. Cool. So we have a 10 newton force down, and now we need to figure out what's our F equals ma. So our F equals ma says that we have a force, and we're going to call this the positive direction, the down direction. So we're going to have 10 over here is equal to, the mass is 1 kilogram, but what's our acceleration term? This is where, hey, the accelerations might combine, because we already did one where there was no, we were just stationary, and then, hell yeah, this thing was moving, and then we said, hey, if this is like 5, this thing still is moving that direction. So sweet. So we're just going to add them up. I'm going to say this is the acceleration F, the acceleration of the actual frame that it's in. So we're going to say the mass is going to be acceleration F plus just the normal acceleration that we're used to, this number. Cool. And that's what we're going to solve for. So we have 10 is equal to 1 kilogram. So see how we still have 10 newtons? So we have 10 newtons. You know, we didn't have 7. You know what I mean? That was a fictitious thing. But we have 10 newtons times 1 kilogram times this 3 meters per second squared plus A. So now we can solve for A, and that's going to be, because this is just going to be 3 plus A, hey, that's going to be 7 is equal to A. So acceleration is 7 meters per second squared. And so that was the technical way to do it, is like, hey, you have to kind of find the, I think it comes from this, hey, sum of the forces in maybe the y direction is equal to mass times sum of the accelerations in the y. So because we have kind of two different accelerations, we have the frame accelerating, and then this inside the frame will be accelerating in reference to the frame also. So that's kind of fascinating. But heck yeah. But I made this video just from the standpoint that I'm definitely going to use this idea of like, hey, can I get a problem simplified? And so, and how does this go back to this scenario? Is like, heck yeah, I want to simplify this problem as a pivot out to a mass. But this thing moves after 1 second. This pivot point moves down. That's the same thing as this. You know what I mean? Hey, this is time 0, and then here is times equals to 1 second. This pivot totally moved down here. You know what I mean? So, and that affected our answer. You know, when we said it had an effective force of 10 newtons, no, it didn't. It was basically an effective force or a driving force of 7 newtons. And so, so that was interesting. So, and it's even interesting that you can do that. You can take a problem where you have a 10 Newton mass, or you have a mass of 1 kilogram, which has a force because you got the Earth underneath us, but then the reference frame is also accelerating, and so you can just, you know, turn that off like a spigot, you know, just by using some sort of ratio that's fairly simple and intuitive, and be like, no, this is like a stationary problem, where this is, or at least stationary that this is bolted to a wall, where now the force is 7 newtons on a 1 kilogram mass. And so that's the intuitive thing that that I would like to propose, is that I'll use for other problems. And I haven't actually done one problem this way with like success yet. So that this because I've never actually incorporated the fact that this is accelerating, and then how that kind of manually adjusts these forces, you know what I mean, in some sort of effective way. Because now this problem isn't, this problem becomes, hey, now this thing's on a track, it's here at 1 second, I mean, it's here at, you know, time is equal to 0, but then it's here a second later. And it still might go down like this, but because it's accelerating, it's going to go down less. If it wasn't accelerating, hell yeah, that thing might be way down, you know, way down here. So yeah, so that's yeah, this is cool, and that's it. You know what I mean? I still haven't done it with a problem with success, but I think you know what I mean, just doing it with this way intuitively, and then double checking from the technical standpoint, I think it flies. So cool. So thanks for joining me, and that's a video.